Theorem 29. It says the perpendicular bisectors of the sides of a triangle meet in a point which is equidistant from the three vertices. This is quite an awesome proof here, and it's incredible how it all works out. But in essence, we're stating that these will all intersect at one point. They all meet in a point, and that point will be equidistant from all three vertices of that triangle. So let's just get right into it. We have a triangle ABC, and we have three perpendicular bisectors. Z, this line Z, is the perpendicular bisector of this side, and Y is the perpendicular bisector here, and X is the perpendicular bisector of AB. We're trying to prove that they will all three meet in one point, and that point is equidistant from all three vertices. So we have our given number 2. I'm going to say some very basic things. And again, if you're just starting off with geometry, it almost sounds like, why do we have to say that? That is so common sense, or such common sense. Why do we have to say it? We have to say really almost everything. The more rigorous of a course you are in, the more you do have to say in your proof. But this is what we're going to say. We're going to say AB, BC, and CA are not parallel. Duh. Number 2 reason, that's the definition of a polygon. The definition of polygon says that the sides intersect, that they meet. So it's a closed figure, which means lines intersect. And so since this is a triangle, those lines are not parallel. We're also going to say that line X, Y, and Z are also not parallel, because we've learned that perpendicular or lines perpendicular to non-parallel lines are also not parallel. Number 3, lines perpendicular to non-parallel lines are not parallel. Number 4, now let us start talking here. X and Y intersect at O. I'm going to say X and Y intersect at O. So I'm just going to extend these lines X, X, Y. Alright, so we can say that I didn't necessarily need to draw those lines, but we're going to have a point where those two lines intersect. And we can say that because two lines, let me write this down, two lines may intersect at but only one point. There's only one point that two lines can intersect at. And so we know X and Y have to intersect somewhere there. So let us now draw some auxiliary lines. We're going to draw AO, BO, and CO. Number 5, 2 points determine a straight line. So let's quickly draw those auxiliary lines where we're saying we are drawing AO. Let's label that point O. We're going to draw BO, and we're going to draw CO. Alright, so we had that point because X and Y, if we were to extend X and Y out, they would intersect somewhere. It could have been over here, it could be over here. I just kind of eyeballed it there and made it decently close to where it needed to be. And then now that I have this new intersection point, I created this point by these two lines intersecting. All I did was now use this point C and this point O and made a straight line. We can do that. And so now we just are having all three of these vertices going to that point O. We haven't said anything about Z yet, but we can state some things about AO and BO and CO. Alright, let's say that AO, number 6, AO equals BO, and BO equals CO. This is from the previous theorem, I believe, as stating that every point in the perpendicular bisector of a line is equidistant from the ends of that line. So let's quickly look at here. We know that O is in the perpendicular bisector of X. We have stated already that X is the perpendicular bisector of X. We said that these two lines will intersect somewhere, but O is in the line X. And so if any point in this perpendicular bisector of AB, we can say that that point is equidistant from the ends of that line. So that's pretty incredible. And O is also a part of this perpendicular bisector of this line. So if this point is in a perpendicular bisector of that line, it is also equidistant from the ends of that line segment. And so we are using the previous theorem, I believe, or even corollary, I can't remember at this time, to help us prove this. So I can say that those two line segments equal certain quantities, AO equals BO and BO equals CO, because any point in a perpendicular bisector of a line is equidistant from the ends of that line. Pretty awesome. But we can now use a lot of our kind of thinking that we've done in the past. And this is where it just like kind of blew my mind when I saw this. Number 7, I can say that AO equals CO. Now this obviously makes sense here, that because since they both equal the same quantity, BO, then they have to equal each other. Quantities that are equal to the same or equal quantities are equal to each other. But when I came up here, what I just said was that AO is equal to CO because of what I said here. Those are equal to each other. Those are equal to... We haven't even said anything about this, but we know that this will be equal to that because of substitution. And the next step is just going to really bring it home, obviously. Number 7, I was able to say AO equals CO because of the substitution axiom. And then number 8, I can say that point O, let me capitalize that, point O also lies in Z. And let me lowercase that because it's a line. Z. Number 8, let's see what I just said. I said that point O, it lies in this line Z. Why in the world can I say that? It's the converse of that theorem that we just used over here. If a point is equidistant from the ends of a line, it must be in the perpendicular bisector, which is amazing. That is absolutely incredible how that works. Every point equidistant from the ends of a line lies in the perpendicular bisector of that line. Pretty incredible. We can make these two intersect at one point. We can draw some auxiliary lines. And if this point is in both of these perpendicular bisectors, it means it must be equidistant from the ends of the lines that they're perpendicular, respectively. And so then we can say that's equal to that, that's equal to that. Since these two are both equal to the same line, these must be equal to each other. And since this point is now equidistant to the ends of this line, it must lie in this perpendicular bisector of CA or AC. Pretty incredible proof there.